Well, good morning. It's 8:32 on Tuesday, the 11th of June, 2019. This is supposed to be differential equations class, and right now I'm the only one in the room. I'm 2 minutes late getting started. Sorry, I was waiting for someone to show up, but they haven't yet. Hopefully they will. Here's a pretty important announcement I have to make, but I'd rather wait until someone is in the room to make it, so I'm certain at least somebody will hear it. So with that said, let's just get going on the where we left off last time. And for some reason, my computer is just jumping all over the place, and I thought I'd already hit this once. The plug on my computer does not make great contact anymore, and I don't know if this is what's being recorded if you see this flickering screen, but I assume that's because of it. Either that or just the old computer is wearing out, which could be the case too. I know the feeling. But anyway, we'll go from there. When it projects onto the screen, usually it's pretty stable, even though it's flickering like crazy on my screen. So I don't know which of these feeds is recorded, the one from my screen or the one that goes to the projector. But anyway, if it's that way, sorry about that. It's on mine as well, and it's probably because of mine. All right. I'll wait and say the announcements later. Okay, I normally would ask, are there any questions, but no one's here to ask, so let's continue. We're in Chapter 2, First Order Differential Equations, and we're in 2.1, Solution Curves Without a Solution, which is a sort of strange title, okay? We had talked about earlier in 2.1.2, autonomous first order differential equations, and that's where we are now. Example 3 is an example of one. Here's a differential equation, and this looks like one we might have seen earlier. Let me get my pen set up. Okay. Now I have to periodically stop and check and make sure the connection's still working, because yesterday, middle of my second class, suddenly the contact didn't make anymore, and I was running on battery, and the battery's weak, and it almost ran down. So periodically stop and check on that. Here's a differential equation. dP dt is equal to P times A minus B times P. No, I'm sorry. Put the parentheses in the wrong place. Didn't think that looked right. All right, like that. Now, obviously, as the chapter says, this is a first order differential equation, and certainly ordinary differential equation. However, this one is not linear. Okay? It may not be completely obviously not. Obviously, dP dt is first power. That's fine. But here, this is a P, there's a P, but you see when they multiply together, that would give you a P squared. It'd be AP minus BP squared, because you have the dependent variable at a power other than 1. That is not linear. But that's sort of beside the point. Here, I think, and here we have a student. Fantastic. Carlton is here. Okay. All right. And today is the 11th. Good deal. Now, I hesitated on the announcements. Oh, I won't start on the projection channel until at least a student was here to hear the announcement. Ethan Hilden's here. He's not going to be here today or not. Charles usually comes in, but he has work issues. And we don't have projection yet, but it's coming. But let me go on and make at least two announcement type things now. And it's been probably close to a week, not a week, since I put your attendance in last. I probably didn't even pay close attention then. I don't know, there's only 6 of you in the course, and I don't know if all 6 have completed payments. In most of the classes, there's at least 1 or 2 people who haven't. I don't know about this class. But they haven't said when this is going to happen, but always they just sort of, and it's random, they'll just suddenly say, okay, all unpaid students will now be taken off the rolls. So if there is any issue, I'm talking to people on the recording as well, any issue that has kept you from paying, please try to resolve that issue. And if nothing else, go to the cashier's window, the business office somewhere, and let them know that what the plans are and that you are working on getting the payment done. Okay, so that's sort of a minor thing. Here's a thing that's a lot more critical to this class. On Thursday, day after tomorrow, I have eye surgery on this eye. I'm having a cataract removed and replaced by a lens. So I will not be here Thursday. I don't know what time it's going to start, but they usually start pretty early in the morning. So I know there's no way I'll be driving out here and then turning around and going back. So they'll probably have us there before this class would even begin. So, but I don't know. They wait till the day before to tell you the time of the surgery. So I just know that I do have surgery on Thursday, and then after surgery, they don't want me driving. They don't want me doing anything that stresses at all on the eye. So basically, won't be coming back Thursday later in the day. So that leads to an issue, and since you're the only student here, you get the car. Now, some of the others, if they come in, they'll get voices too. There's a couple ways I hate it because it's my fault we're missing the class. We can try to make up the class by going class a little, either starting a little earlier or going a little later, if that's convenient for y'all. Or the other option is go to the YouTube videos and pick up where this class leaves off and hit that video and then come back at the end of that one. So either of those are a possibility. If we choose to extend the class either on the front end or back end, we could do it over a period of classes. We could do as little as 15 minutes. That would take, this class is what? An hour and 15 minutes. So that would take 5 classes at an hour and 15 minutes each. We did a half hour, that would be 3 classes, we would get that done then. If we did, a full class, that would be a possibility too. I don't care. Do you have a preference?
No, I don't have a preference, but I can use YouTube videos that work. If they're like same as class time, we can use YouTube videos.
Use the YouTube video I did before. Now, it won't be as long a class, but it'll pretty much cover.
Book, I think that plus the book.
Yeah. Okay. All right. Well, that's the vote we have so far, and if no one else comes in, that's what we'll go with. So not extending classes, but just using the YouTube video. Right? Is that what I understood? Okay. All right. We're on example 3 at the top of page 40, if you do have a book. And this is on an autonomous differential equation. I was just mentioning this certainly is an ordinary differential equation. Those are D's, not partials. It's a linear differential equation. I'm sorry. It's a first order differential equation because this whole chapter is first order. Oh, the 10 o'clock scholar. Okay.
Only 15 minutes.
Pardon me?
Only 15 minutes.
Oh, I'm just kidding.
So,
Okay. All right.
gas.
Huh?
Gotta get some gas.
Oh, I see. Okay. So where did you eat for? No, I was just kidding. Okay. All right. I just mentioned to Carlton, pretty important issue. I have eye surgery on Thursday, so I will not be here at all on Thursday. It's cataract. Just had my cataract removed. I had it done in the right eye more than 9 years ago. And usually they're close together. Mine was far apart, 9 years, almost a decade. But I'll have that surgery on Thursday. Probably in the morning. They haven't told me the time yet. But I think he schedules all his appointments in the mornings. And then he monitors during the day. So I'm pretty certain I will not be here Thursday at all. We're just talking about the options. I hate, because it's my fault we're missing class, not school canceling or something like that. So how to make up the time, and there are a couple of options. We could either start a little earlier, which doesn't seem like a very popular option. We could go a little later and spread it over as many classes as we wanted to, or you could do the YouTube videos from last time. That I taught the course. It won't be as long as this one, because that was an hour and 15 minutes rather than 2 hours and 15. No, actually it's 2 hours 15 minutes. I was saying that wrong before. 2 hours and 15 minutes. So, what would be your preference?
So the options either YouTube videos, or one day like we extend the class to go back over it.
Yeah, or just extending this class, and we could do it as many days as we wanted to. We could spend 15 minutes a day, and that would take us 9 class periods to cover everything, make up. We could do a half hour at a time.
We could just do the YouTube.
Or do the YouTube.
Since it's already out there.
Okay. Now, the only issue with it, the YouTube is an hour and 15-minute class rather than a 2 hour and 15-minute class. So, but yeah, it'll cover at least some of the stuff, and we'll pick up and go from there. So is that that's what Carlton wanted to do too. So,
whatever's easier for you.
Doesn't matter. My Tuesdays and Thursdays, I'm open. I can go longer, or I didn't know if you had other classes or work or other things like that would be inconvenient to do. The YouTube videos are always an option. So you want to go with that?
Yes, sir.
Okay, at the end of class today then, we'll see where we end. I'll go to the YouTube videos and pick out and tell you this is the one, or maybe 2. If one of them covers part of what we've already covered, then we'll do the end of that one and begin and the whole next one or something like that. So we'll do that. Remind me at the end of class.
Yes, sir.
And both of you did get your test shot.
Okay.
Yeah. Technically a week, but you can have more if you need it. Now, what I don't want is for it to still be out when I give the second test. Okay. Now, and here's the other thing I forgot, because it was at the end of a class last time. Yes?
Has Cal 3 dropped the test yet?
It's what?
Cal 3? No.
No, probably we'll have that test tomorrow. I'll be ready tomorrow. I don't have it up here now anyway, but I don't think it's run off yet.
Okay, that's fine. That's fine. I just didn't know. I didn't watch yesterday's YouTube video.
Right. So yeah, I think we'll finish that chapter tomorrow.
So if you're not going to be here Thursday, I can just pick up that test next Tuesday.
Yeah, that'll be fine. Yeah. Okay. Or if right after class you want to go down to my office, I'll get it for you then, whichever you prefer.
Tomorrow.
Today. Or tomorrow too. You're not on this campus tomorrow, though, are you?
No, I'm on.
Yeah, okay. So if you want to get it today, the test is made out, it's just not run off yet.
I think next Tuesday.
Next Tuesday. I thought that might be the choice. Okay. I don't know how I thought that, but somehow I must be psychic. So.
I got a lot of homework.
Yeah, okay. All right. Now, was there one other thing I don't recall now? If there was, okay. Oh, yes, I did. There was one other thing. Carlton, you didn't get to hear it. I started receiving a little bit of flack from some of the other instructors because I do give take-home tests in my upper-level courses, and they typically don't. Of course, they don't teach the same upper-level courses I do. So I've always suggested it. Now I need to require it. I need to see all the work, okay? Especially that first test in this class. It's verify this. So many of the questions, verify this. You can't do that with just writing down an answer because the verification is a process. So for all of them, whether they're just taking a derivative or whatever, you need to show me all the steps. The gripe from the others is, they could be getting at other sources and not even know what they're talking about. So yeah, you need to show me all the steps. And that will be on the calculus test as well as this. All right. Any other any questions?
Is this 2.1?
This is 2.1, and more specifically 2.1.2. 2.1.1 was those diagrams, direction fields, and 2.1.2 is autonomous first order differential equations, which is what we got a sample of here. This is example 3, top of page 40, if you got your book. Okay, as I was just saying, I said it before Carlton came in, and I said it when Carlton came in, and I'll say it again when Nolan's here. This is a ordinary differential equation. Those are these, not partials. It's a first order differential equation. Obviously, this is just first derivative. That's the only derivative in it, so it's first order. And the whole chapter is on first order differential equations.
Linear?
Okay, good point. Is it linear?
Yes.
Why?
Because there's no exponent.
No exponent on the first derivative. But notice this.
Oh, wait.
Yes.
It's
If
on.
you multiply through, that would be a times p minus b times p squared. So it wouldn't be linear.
I see B.
Yeah, but it's not. That's not an issue on this one, but I just wanted to bring that to mind. Even though you don't see the exponent, when you multiply through, you would get an exponent. So, glad you brought that up. All right, a and b are any positive constants. Now, they say it has the normal form. Why they call it normal, I'm not sure. That dp dt is some function f of p and p alone. In other words, the independent variable is not at play. You're taking the derivative with respect to it. The p is a function of that, but that independent variable doesn't show up in the equation anywhere else. Okay? So this is just a function of p. Now, I also wanted to say this. I said it before anyone came in. My computer, where it plugs in back here, there's not a good connection there. And I have to work with it when I first plug it in every morning to even get it to make contact. Once it does, it usually makes decent contact. Now, what's happening now on my screen is not quite strobing, but it's just going in and out at random intervals and not in a very regular pattern. This is showing up very steady. So I don't know what it's like at home. I don't know if the YouTube video is recording this or that, okay? But, and part of that is because the connection makes and doesn't make. I can see the lights sort of blink a little bit every now and then. And yesterday, second class, it just went out and I didn't notice it, and I was running on battery. Everything was getting weak, and then I had to fiddle with the plug again.
I think it works on the YouTube video because it's different. If that stream's perfect.
Okay. All right. Well, good.
It's just your screens.
Yeah, that's what I'm thinking it is, but I didn't know what feeds to YouTube video. So it's probably more what you see here. Okay. But I just didn't know. But then, of course, that can be malfunctioning too, and that wouldn't influence the YouTube video. All right. So anyway, here is our differential equation. Okay. And I don't know, was I saying x before? T is the independent variable, not x. Okay? T is the independent variable, P is the dependent variable, and so this is an autonomous differential equation. Again, to remind yourselves what an autonomous differential equation is, from the previous page an ordinary differential equation, which this is, in which the independent variable does not appear explicitly, is said to be autonomous. The independent variable here is the t. It doesn't show up anywhere in the expression here except that you're taking the derivative with respect to that. All of the dependence here is on the dependent variable. So that is a autonomous differential equation. Okay. Now, flip the page on me. Okay. Now, there's this f of p. This function, f of p, is what this derivative is. What does the derivative tell you?
If it's increasing or decreasing.
Okay. In other words, it's the slope of the tangent line, right? That's what those direction fields are telling us. You may not know how to solve it or anything else, but that shows you this. So this says the first derivative, the slope of the tangent line, is a function of p only. Not a function of the time, only a function of p, whatever, or t may be something else, but that p could be pressure, it could be population, it could be whatever it is, the derivative is only a function of that. I mean, obviously it's a function of t, but the only explicit expression here is with the p's. So, what do we usually, when we're dealing with derivatives, slopes of tangent lines, like you said, increasing, decreasing, what are usually the points we consider of interest?
Zero.
The zeros of the first derivative. And we call those the, this is going back to Cal1, a long time ago. Say again? Well, yeah, you use them to get maximum. Critical points, yes, the critical points. So, where would this derivative be zero? What would be your critical values? Now, usually, that's with respect to t. Now we're doing with respect to p.
Only if p was zero.
If p is zero, that's going to give you a zero. Absolutely. So we have a critical point at p equals 0. And one more.
Somehow like a minus bp was 0.
Exactly. A minus bp equals 0. That would be the second one. So solve that for p, and what would you get?
P equals a plus, or a divided by b.
Yeah. I mean, take time if you want to. Add bp to both sides. You get a is equal to bp, right? And then divide by b. P is equal to A over B. Okay? So those are your two critical values. Okay? Now, and then when you were saying increasing and decreasing, that's what you said when I asked what's the importance of the first derivative. You said it shows whether it's increasing and decreasing. What does that tell you? How do you know whether it's increasing or decreasing?
You took the second derivative.
Okay, but just looking at the first derivative. What would be true?
Positive.
Yes, the first derivative would be positive. It's increasing, and negative it would be decreasing. Okay? So where is this function most likely to be positive? Okay, now let's see if they told us anything about this. As far as I know, they just said A and B, yeah. All right, here's Charles. Okay? Now, they may have already outvoted you, but you do get a voice in it if you want to. Good deal, thank you. Okay? Already given me papers to grade. Wow, thanks so much. Okay, now.
What was the vote?
Was that?
What was the vote?
Yeah, we'll get into it now. On Thursday, I know you said some Thursdays you won't be able to be here, but on this coming Thursday, day after tomorrow, I have to have a cataract removed in my left eye. Okay, so that means I will not be here at all on Thursday. Okay, So we talked about how to make up the class, because it's my fault it's missing, not the school's fault or anything. So I'd like to make sure that y'all you paid for the instruction, you should get it, right? So the options were, we could start a little earlier, which doesn't seem like a very popular option. We could go a little later, and we could stretch this over as many days as we wanted to. Or you could watch a YouTube video that I did the last time I taught the course. Okay? So which option would you prefer?
YouTube video?
That's what everybody else has said, okay? I notice how much y'all enjoy my instruction, okay? It doesn't hurt at all, though. I mean, I'm fine with it. Okay, so we will do that. At the end of class today, we'll stop, and then I'll go show where on the YouTube videos that we'll do, and say this is a 1 or a 2. If where we end today is in the middle of one video, we'll finish that video and do the next one, or something like that. We'll talk about that at the end of class. Okay? All right, good deal. Okay. Now we were doing example 3, top of page 40. Not going to go through all of it again, but what we've done here is we notice this is an autonomous first order ordinary differential equation, not linear, but that's beside the point here. And we found our 2 critical points where this first derivative is 0. The critical points are at p equals 0 and p equal a over b. Okay? So we've determined that. Now the question was, can we tell from this where the function is increasing or decreasing? What gives that away?
If it's positive.
Second?
Didn't we just say if it's positive?
Okay, if what is positive?
P?
Not p.
The derivative?
The derivative. If the derivative is positive, this is going to be an increasing function. If it's negative, it'll be decreasing. So, here we know the p is 0. Okay, at p equals 0. Here p is 0 the derivative is 0. Derivative is 0 at p equals 0. Derivative is 0 at p equal a over b. Now, what we don't know, because we don't know the signs of a and b, and that's what I was looking at when you walked in. Here they do say it. A and B, positive constants. They just happen to tell us that. And right under the expression here, they say A and B are positive constants. Okay. Now, what they don't say is which is greater or lesser. Okay? But that doesn't really matter too much. Okay? Because if both A and B are positive constants, okay, then P is positive here, P is 0 there. So between here and here, P is 0 here, positive here, the indication would be that it's positive between here and here, okay? Because there's not another 0 there. Right? So this must be an increasing function between p equals 0 and p equal a over b. Now, at a over b, since this is a critical point, and we sort of just assume this is going to be a change of direction there. Now, it doesn't have to be, except for this. Okay? For this to be 0, okay, that almost requires the a equals 0, doesn't it? I'm sorry. The slope is 0 at this value here. Okay. Now, slope is 0 there. Now, going beyond a over b, something greater than that, a is getting larger. B is increasing between 0 and this is a positive number. we're assuming this is going to be positive. Beyond that, if it's turning around, then this must be this is always positive, but the derivative must be negative. So derivative is 0 here, and it could be 0 like this, or it could be any kind of a form here. But because a over b is positive, then between 0 and a over b, this function is going in one direction or another. Let's assume positive there. Then if the derivative is 0 here, that must mean the first derivative goes negative here, the first derivative. Now that would indicate to me that then b would be greater than a. Okay? So this would be at smaller values of p. If b is greater than a, and b and a are both positive constants. Okay? And then that's going to make the derivative negative. If a and b are both positive constants, p, well, I guess p could be negative too. So anyway, you have to play around with the different things. You have a boundary, and this is what the book goes into next. Okay? Okay. You've split your p. Now remember your t is your independent variable, and this is your dependent variable p. Okay? At p equals 0, and I should, okay, I've drawn this poorly. Let me erase this. Okay? Because p is not guaranteed to be positive. I drew it as if it was. Let's put the line up here. Here's the t-axis here. Okay? When p equals 0, this is where you are. And here, your derivative is 0. So let's just go on and draw in our little arrows. Okay? We know that the derivative is 0 where p is equal to 0. Okay? We know the arrows are 0 there. 0 slope. Okay? Now, a over b is positive because a and b are both positive. So that's up here somewhere. And we don't know where, but I'm just going to arbitrarily pick a place. And here is where p is equal to a over b. Okay? And here again, the derivative is 0. We know that. Okay? From our analysis down here. Okay? Now, what we don't know is what it is in between these two. Okay? Let's see if they tell us any reason. Okay? By putting the critical points on a vertical line, which is our p-axis here, we divide the line into 3 intervals defined by negative infinity, that's going this way, to 0, that's one portion, 0 to a over b, that's this portion, okay? So you have this region, and this region, and a over b to positive infinity there, okay? Now, the arrows on the line shown here indicate the algebraic sign of f of p on those intervals, and whether a non-constant solution is increasing or decreasing on the interval. Okay? So let's do some figuring here. They show that this is decreasing here, and it's increasing here and decreasing here. Now let's see where they get that. Okay? Here your slope is 0. Okay? Obviously, p is equal to 0. There it's 0. Now, if you go down here, p is negative. Okay? And we don't know about a minus bp. okay, whether that's positive or negative. But P's negative, and if this P is negative, or of course it's the same P, so then this is going to be, B is positive, that's going to be positive, that's going to be positive. So if P is negative, then this is going downhill here. So it's a decreasing function here. Therefore, okay, let's use that same reasoning. P is positive here, and A minus BP, P is positive here. And there's no guarantee that it's increasing here, but it would just seem to fit. If it's decreasing here, you would think it would be increasing here. And if P continues getting larger, then this, of course, is positive. P gets larger, this is going to soon outweigh this. So this term is negative. So the product is going to be negative. So that's going downhill. So it only kind of makes sense. This has to be increasing here. Sort of hard for it to be decreasing everywhere and you still have zeros. I mean, it can happen. Function can do this and that, but that's not very likely. So the odds are it is going positive there, okay? Because P is positive, so the first term is positive. A minus BP, yeah, it's, I guess it could be that the B was enough, well, for very, very small P's, then that term's going to be pretty small, so A is probably going to be, yeah.
So if A and B are constants, right?
Yeah.
How can you, I mean, would they equal the same?
No, I wouldn't think they'd be the same, because if they were, well, nothing keeps them from being the same, but the thing is, whatever they are, they're positive, okay?
Wouldn't they be, I mean, as B gets bigger, or if B gets bigger than A, wouldn't it be decreasing?
Okay, yeah, and that's the point here, okay. They're staying the same, but even if B is larger than A, but A is positive, if P is near zero, okay, then this is going to be a small term, and A is probably going to win. Okay, you can get small enough in P, so this is less than that. So this will be positive. So somewhere in here it's positive, and then here it's zero again. But then after a while, with P increasing, A and B are constant. P increasing, somewhere up here, this term gets bigger than this one, so this has to be negative. So yeah, this is set up correctly. Even if this is a really small range there, if B is a great deal larger than A, it's just really thin here, because A over B would be a very small number. But in that small interval there, this is positive. So we'll just take it to be here. Now, with that in mind, you know the slope of the function, it's 0 here, positive here, 0 there. Negative going to 0, and negative, going to 0 here. Okay, we don't know which way it's heading here, but it's 0 up here and negative here. So it has to be decreasing here, decreasing there, and increasing there. So this is what the function looks like. Values in here, values in here, values in there. Really, it's not much of a function because it can take on different values depending on the size of P. Okay, this is what it would be. Okay, now, so the sign of f of P is minus down here, positive here, and minus up there. Okay. Now this is what we call a one-dimensional, okay, forget what I drew there. Just look at the y-axis here, the p-axis here. That's called the one-dimensional phase portrait, okay? You got a 0 here, a 0 there for slopes, okay? Negative slope here, positive slope there, negative slope there. that is a one-dimensional phase portrait, just that p-axis, okay? Now, your solution curves, I went on to this. This is what they would look like. But they jumped to a completely different problem there, but I did the one here. If you want to go back to the problem, that's what example 4 does. And this is the picture showing example 4. Okay? So we'll come back to that a little bit later. Okay. Except, not quite example 4. I showed it that it was all positive. T doesn't always have to be positive. If T could have been negative, this could have been coming down here. This could have been going like this here, and this could be going like this here. And we don't know where it's heading there. They show it just keep going down. Okay? We don't know. But that's example 4. We'll get back to it. Okay, I don't know why they wouldn't have continued and done it here, but now they jump over and look at something else. Okay? And these are solution curves, and without solving an autonomous differential equation, they seem to love not solving them. We can usually say a great deal about the solution curves, and this is going to be a new problem here. They did example 3, jump into a new problem here, and then they're going to come back to example 4. Why they're jumping all over the place, I'm not sure, but that's what they're doing. Example 4 is revisiting 3. So let's now remember this, because I have to erase it, and we'll have to reproduce it later. Let's erase this, and we're going to do the new one, solution curves here. We're looking at a function f in that first thing, independent of the variable x. We may consider f defined for, so we're going to say f is defined for minus infinity, less than or equal, not less than, there is no equal to infinity, x less than positive infinity. Just assume it's defined everywhere. Okay? Now, or we could define, as they say here, 0 is less than, do they put the equal sign there? Yeah, they put the equal sign here, x less than infinity. Whatever your interval of interest is, it is. Also, since f and its derivative f prime are continuous functions of y, okay, now we're going back, not talking about p's anymore, but y's, on some interval on the y-axis, the fundamental results of theorem 1.2.1, which was previous, I'm sorry, chapter 1. You can go back and look at that if you want to. Hold on some horizontal strip or region R of the xy plane corresponding to R. A lot of blah, blah, blah here, okay? Let's just see if we can get to what they're talking about. Okay, here it is. For the sake of discussion, let's suppose that our equation, whatever that is with f of x in it, possesses exactly 2 critical points, C1 and C2, that C1 is less than C2. So here's going to be our y-axis, and here's going to be C1, didn't they say, was less than C2. C2 up here. Okay? May have drawn it too far up, I don't care. Okay? Now, they don't say anything more about this except that C1 is less than C2. The graphs of the equilibrium solutions, y is equal to C1 and y is equal to C2, are horizontal lines. And that's what I was saying before. That's supposed to be a horizontal line, folks. And that's supposed to be a horizontal line. Okay? And here, the derivatives are 0. Because those are critical points. Now, this is on the y-axis here. We're not talking anything about x yet. These are horizontal slopes, 0 slopes at the critical points. These lines partition the region R. The region R is your whole region here. into three subregions: R1, R2, and R3. Okay, just like we were doing before. Okay? Without proof, here are some conclusions about the non-constant solution y of x for that differential equation that we've been referring to. They call it 2. If x0, y0 is in a region R sub I, one of those three regions, okay? If x0, y0 is in one of those three regions, okay, and y of x is a solution of the graph that passes through that point, then y remains in that region. So if this was your xy, let's just say it was like that last one we were looking at, that it was positive there. If this is your x0, y0, okay, obviously it's going to be in one of these three regions. If it happens to be in that one, then it stays in there. It can't leave the region because you have zero slopes, okay? Or it could have been like this, okay? But it has zero slopes at C1 and at C2. If it happened to have been down here somewhere, then it's either going to be like this or like that, okay? It has to be there. If it was up here somewhere, then it was either going to be this one or it's going to be coming down from above and flattening out. It can't jump the boundary. The boundary are where your slopes are 0, C1 and C2. Okay? By continuity, F must either I don't quite see where they're getting this one. But it's your slope. The slope doesn't change sign because it was 0 here, 0 there, and if there's no other zeros, it can't change sign. It can't. If it's a continuous function, the first derivative is a continuous function, it can't go from being positive to negative without being 0, or from negative to positive without being 0. So the slope is all either increasing or decreasing, monotonic within each of those areas. We don't know which, and they can't cross. Okay. Since it's either positive or negative in a subregion, then it's strictly monotonic. I just said that. If y of x is bounded above by a critical point, okay, then the graph must approach the graph of the least equilibrium solution y of x equals c1, either as x is going to positive infinity or negative infinity. See here, if this is your point, you're approaching C1, it's either approaching it as x goes to negative infinity or positive infinity. Just like I've drawn here. Same, if the point was up here, it's either approaching the critical point as x goes to negative infinity or positive infinity. Same thing down here. If that's your point, x0 or y0, it's either approaching the critical point as x goes to positive infinity or negative infinity. Okay? One or the other, monotonic, only going one direction within any region. Okay. Now, that's all they're going to talk about. So now we're going to get back to equation 3, which we were doing before, and basically do the same thing I had done, but we'll put our p-axis here. Remember, that's the one with p. So here's your p-axis. We had p equals 0 was your one horizontal asymptote. Okay. And p equal a over b, where a and b are both positive. And that was your other horizontal asymptote. Okay. Function slope is 0 at both of those. Okay. Now, we had already determined p was increasing in the middle here. It's decreasing up here, and it's decreasing down here. Okay? We'd already determined that, but just by our analysis of the A over B. A and B are both positive. If A is a great deal larger than B, A over B is pretty far up here. If A is smaller than B, then it's a pretty small number here. But in that little region, that's got to be increasing, because the P is 0 here, and so yeah, this will be an increasing function here, decreasing in both of those regions. Decreasing here because P is negative, and doesn't really matter what the other one is. And up here, your B is, P is positive, but this is the region where the A minus BP, the P being very large, that's going to drive that negative, but the P is positive, so that makes the product negative. Okay. So that would be what our picture looks like. Okay? Only in this region and this region is P bounded from above. Up there it's not. Okay? So therefore that can go toward infinity. It doesn't matter. But here, bounded from above, so it has approach to horizontal asymptote when X is very large. Here it's bounded from above, and this is approaching horizontal asymptote when X gets very, very negative. Positive there and negative here. Okay. Now, those are our three regions. Let's name them the same way here. Region 1 was from minus infinity less than P less than, do they put equal? No, they just put less than 0. Here is your region 2, and this is where 0 is less than, and yes, they do put, no, they don't even mess with the equal sign at all in any of them. Because in reality, they just approach, they don't really, yep, it didn't take. Okay, that time it did. Okay, less than P, but P is less than A over B. And up here, this is region 3, and here P is greater than A over B. Okay. This is your t-axis here. All right. So this one, as t approaches negative infinity, in this region, the p is approaching 0. In this region, as x approaches t is approaching negative infinity, your p is approaching 0, and as it goes to positive infinity, it's approaching a over b, and up there, as t approaches negative infinity, it can do whatever it wants to. It's increasing without bound. Okay, so it can go up slowly, rapidly, it doesn't matter. It has to keep going up in this direction, actually down here, and then it approaches a over b as t is approaching positive infinity. Okay. Now, again, they spend an awful lot of time on this, and I guess it's worth it. Okay, I shouldn't be minimizing this. Let's do example 5. And you know what? I've been thinking, I've been drawing all these graphs, and all I had to do was this. Wait, I went the wrong way. Previous. Okay. That's what I knew. Well, they should have been using the graph already rather than me doing it. Okay? Here's example 5. An autonomous equation, and here we have it, dy dx, going back to x and y, so this is your y, this is your x. Dy dx is equal to y minus 1 squared. Okay? Now, ordinary differential equation, those are D's, not partials. Yep. It's first order differential equation, yep. But is it linear? No, because the y, this would appear to be linear. It's just to the first power. But here you have a y squared. If you expand that binomial squared, you get a y squared. So that's not a linear equation, differential equation. Okay? Not that that matters too much at this point. Now, where are some critical values? Do we have any? In other words, where is the derivative equals 0?
At 0. Wait, is that a squared? Y minus 1 squared?
Yeah, y minus 1 squared. So where is this derivative equals 0?
Plus or minus 1.
Okay, only at plus 1. Yeah, if that had been y squared minus 1, that would have been plus or minus. This is y minus 1 squared, so that's at 1. And just so I can do it, let's just make this 1 and this 2. This is minus 1 and minus 2, just to expand the graph a little bit, okay? So this is at y equal 1, and that's the only here. So here's your horizontal asymptote. They don't call it this, but this is the place where the slope of these is 0. And that's the only one you got, okay? Slope is 0 there, okay? Now, what can you tell me about the slope elsewhere?
It seems like when you put would it be decreasing? Because every time you put like, if y equals 3, x is going to equal 2.
Okay, say that one more time.
So, if you put in like y equals 3 and it minuses 1, oh wait, but it was square, so it increase.
It's increasing everywhere because of that square.
Yeah.
So when y is less than your critical value, 1, it's increasing. When it's greater than your critical value, 1, it's increasing because of that square. So you're thought through it well, huh?
So if it didn't have the square, though, it would be decreasing?
It could be. If that was just y minus 1, then it would be increasing for y greater than 1, decreasing for y less than 1. Because you see, y less than 1, I'm sorry, I said that backwards, didn't I? No, I said it right. Y greater than 1, this is positive, if that's 0, if that's 1 up there. And y less than 1 is negative. So then it would be decreasing here, increasing here. But this is increasing in both places. So it's doing this up here and this down here. Okay? So we just don't know where until we know one point. That's where we need our initial value problem. We need a point. Once we know a point, then we can draw the curve that goes through that. But this derivative is always increasing. Increasing here, increasing here. So the function is increasing everywhere, whatever its value is. Okay? Now, they say for an initial condition, y of 0 is equal to y0, with that y0 being negative. So if you have y at 0 is equal to y0, but this is a negative value, that means you're down here somewhere. So when x is 0, you're down here at some negative y0, say here, just to pick a point, okay? Now, it has to be an increasing function because your derivative is positive, and it has to be approaching up here. So this curve, wherever it's coming from, has to go through that point and then approach that line. Okay? Never crossing it. Mine crossed it. Shouldn't have. Shame. Okay? But it's doing that. So that would be that value. Now, they've done something else here that's bizarre, and I'm trying to figure out why. Oh. They've jumped to a completely different problem here. Sorry. I was wondering, how in the world did they get that? Okay, they didn't even draw the graph here, but they did. If this had been the point of interest, or this one or somewhere like that, then it would have been a line that goes through here. Okay? Approaching the horizontal axis, asymptote as x goes to negative infinity. Okay. Now, they jump to a completely different problem. Sorry about this. I don't know. Sometimes what did you just do? Okay. It is just, okay. Let's go back to here. Okay, I have no idea what this thing is doing here. It's just sort of got a mind of its own. Okay, now let me see if I can get it to erase this time. I went to do this last time and it just went black. Okay, power's still on. Okay, here's a new problem. I was thinking, how did they get this? Here we have a new function. Y of x is equal to 1 minus 1 over x plus c. Okay? No, it's not a new problem. They say that is a solution to this differential equation. dy dx is equal to y minus 1 squared. Okay, now they say we've done this before. See problem 4 of exercise 2.2. No, we haven't. We haven't gotten there yet. So they're just sort of jumping all over the place. Okay. This is what sort of drives me crazy about this. They started with this and just talked about some things in general, and then suddenly jump to that and says it's a solution to it. Are you convinced it is, or you need some proof? Huh?
Need a little proof.
Yeah, let's do it. So let's take the derivative of that, okay, with respect to x. All right? I hope I wrote the problem down right. I think I did. Okay? dy dx is equal to the 1 gives you nothing, right? And I'm going to rewrite this, I think. 1 minus x plus c to the minus 1. I just like taking that better. So the derivative of 1 is 0. Derivative of the next part would be a x plus c to the minus 2. Wouldn't it? If you rewrote this as 1 minus x plus c to the minus 1, to me that's far easier to take the derivative of that, right? Okay, derivative of this would be, derivative of 0 is 0. The derivative of this would be a minus 1 times a minus 1, which would be a plus x plus c, decrease that by 1 to the minus 2. Okay? Now, here comes the magic part, okay? this is, okay, let's do another thing here. Let's write down y minus 1 because it shows up down here, right? Well, my y minus 1, if you subtract 1 from both sides, this goes away. And that then would become 1 over x plus c. Wouldn't it? It'll come back, yeah. If you subtract 1 from both sides of your original equation here, then you have only, I have a minus sign, missing a minus sign, minus 1 over x minus c. Okay? So, what happens if you were to square this? Right? Then you would square that. And what would that give you? Minus times minus is plus 1 over x plus c squared, which is exactly this, 1 over x plus c squared. So sure enough, your dy dx, okay, is equal to y minus 1 squared. Okay? So, absolutely, that is a solution to this differential equation. Right? Okay. No, this differential equation. The top line is a solution for this. Notice we say a solution. It doesn't say it's the solution, but it's a solution for it. Okay? So, if it's all right, I'm going to erase most of this. Okay? All right. Okay. I did want to show that to you. That is indeed the case. There's our differential equation. There's the solution. And we see that indeed it is a solution. All right. Now, this is the one we were doing before. Remember, we put the 1 here and 2 here, minus 1 here, minus 2 here. Okay? And y minus 1 is your horizontal asymptote. Positive or zero slope all along that. Okay. Have two regions, above and below the line. Okay? Positive slopes in both places. Okay? Now, obviously, x can't equal negative c, right? Because that would make that 0. So we also have a vertical asymptote. X cannot equal negative c. Okay? Now, it depends on what the value of that c is. Okay? If that c is, they show here a negative 1/2. Let's go back to it. Okay. A given initial condition determines the value for c. Okay. I've said that before. For the initial condition, say y of 0 is equal to negative 1. So if here's your initial condition, y of 0 is equal to negative 1. Okay? So when x equals 0, y is equal to negative 1. That means that point is on the curve. Okay? You know you have a horizontal asymptote up here. Okay? You also know it's always an increasing function because your derivative is always positive. So this means this thing has to be going positive here and approaching there. Okay? Now, if you had y of 0 is equal to 2, I'm going to do this in a different color. You pick me a color. Any color. Red, okay. So we'll do y of 0 is equal to 2. That means y of 0 is equal to 2. There it is, right. How in the world did I do that first one? Sorry. I need to erase something here. It didn't erase. Well, not picking up the eraser. Okay. I don't know how I did that first one.
Is that saying when y equals 0?
Yeah, it's -1. That first one should be right here. Let me go back to black. That should be right here. When x is 0, y is -1. So that's coming up and approaching this like this, somehow. Okay? The second one here, let me go back to red. The y of 0 is equal to 2. That would be right here. But we know that has to be an increasing function here, so that means it's coming from here and going up. Okay? Now we just don't know where it's going. These are two different initial conditions, and they throw the function in completely different regions. Okay? Now, let's take that first condition. Let me go back to black. Okay? When y is 0, when x is 0, y is -1. So then we would have a -1 plugging into the function. -1 is equal to 1 minus 1 over x plus c. You know that has to be true. Okay. Oh, except x is 0. 1 over c. Okay. All right. Let's fiddle with that a little bit. Let's add 1 over c to both sides. So you have 1 over c on the left-hand side now. Add 1 to both sides coming the other way is equal to 2. So this says c is equal to 1/2. Would you buy that? Okay. What we do, we took this initial condition here. Here is your function. Put a 0 in for the x. That becomes a 0. And your y becomes a -1. Okay, so -1 is equal to 1 minus 1 over c. Okay, I want the 1 over c on this side, so I moved it over to here. I'll take the -1, add it here, so that becomes a 2. And if 1 over c is 2, c is equal to 1 over 2. Right? Okay, so then your function then is equal to y of x is equal to 1 minus 1 over x plus 1/2. All right. Now, if that's the case, if that's your equation, okay, y is equal to that. Now we know the vertical asymptote has to be -1/2. Okay, so we take our good old handy-dandy, I'm going to use red again, x equal 1/2. That's your your vertical asymptote. Okay, which means, now let's go back to black, that this has to be approaching that vertical asymptote, go through 0, -1, and approaching the horizontal asymptote there. Now, if that's the case, somewhere up here you have the other end of that function. That is a function. It's in that quadrant up there, this quadrant down here. Okay? Now, the second case, you had to choose red, didn't you? Okay? In the second case, y of 0 is equal to 2. So let's do that one, and let's plug that in. 2 is equal to 1 minus 1 over c. Okay? Then we have 1 over c is equal to negative 1. If you add this to both sides and subtract that, then you get this. So now c is equal to negative 1. Inverse of that would be negative 1. Okay? So, in our function up here, y of x is equal to 1 minus 1 over x minus 1. That's now the function. Okay? In this case, your vertical asymptote is x is equal to 1. Now, I didn't put these in, so let me go back to black for a moment here and do 1, 2, minus 1, minus 2. So now here's your vertical asymptote. Now I'm going to put this in red. I'm going to put it in this darker red. I don't know if you can tell it, but there's your vertical asymptote now. And your point is this one up here.
I have a question.
Sure.
So the 2 equals 1 minus 1 over c.
Yeah.
And that in from there, you got that 1 over c equals negative 1.
Yeah. Okay. How I did that was I add 1 over c to both sides, so it moves it over here. Subtract 2 from both sides, that gives you minus 1. Right? Okay. And then flip this and flip that, and you should see it equal to negative. Right? Okay. Is that what you had? Okay, then you put the c equal negative 1 back in here, and this will be your expression. Y of any x then would be 1 minus 1 over x minus c, no, x plus c, but c is minus 1, so it would be that. So that makes your vertical asymptote x equals 1. So that's what I just drew in here, x equals 1 is your vertical asymptote. And I realize now
Could you take that c and multiply the 2 by it? Like, since the
multiply what by it?
Since it's 1 over c, could you take the denominator and multiply that 2 by it? You get 2c equals, no, that would be 2c.
Okay, what did you want 2c? I didn't
Like, you
understand.
take that negative 1 over c.
But right here?
Yes, sir. You see the negative 1 over c?
Negative 1 over c. Like right here?
Yes, sir.
Okay.
Take that c, can you multiply that 2 by it?
Multiply everything by c? Okay, yeah, you could do that. You have 2c equals c minus 1. Right? Okay? Subtract the c from both sides. Yeah, let's do it that way. It's perfectly legal in most states. 2c is equal to, this is, I'm too near the bottom. You messed me up big time. You ought to be ashamed of yourself, okay? As if I'm not messed up enough. It's gone off into Never Neverland. Let me see if I can get rid of that. No, it's... boy. Let's try that and see what happens. I have a feeling it's not going to respond. Let me try this. Nope. So let's... Okay, which program is it? Microsoft PowerPoint. Yeah, that's fine. Let's restart it. Hate that we're going to lose that, but we are.
Instead it'll try to keep it.
What's that?
Instead it'll, if you close it or restart it, it'll try to keep your information.
Okay, we'll see what happens. Microsoft PowerPoint is not responding. I love Microsoft PowerPoint. It's just wonderful stuff, isn't it? Okay. This is wonderful. Okay. I'll close this, I think. Yeah, here we go. Yeah, that's another way to solve that. I did it one way, but this is another way, and that's what I was trying to do. Oh, boy. Okay, here we go. Go back to this one.
You can,
Yeah.
Yeah.
Okay. Is it flickering there? It's not. On mine, it's driving me crazy. It's strobing like crazy. So let's... All right. Let's see if we can go from current slide. See what happens. Okay. All right. Let's go back. I'm not going to recreate everything, but let's at least rewrite what our problem was, among others. dy dx is equal to y minus 1 squared. That was our differential equation. Our solution for it that we verified, y is equal to 1 minus 1 over x. Ooh, that cleared up some. Okay. Plus c. That was our solution, right? We had two of these. We had an initial condition y of 0 was equal to, what was the first one, 1?
I think it was negative.
Negative 1, you're right, negative 1. Okay, and I realized later I graphed that wrong. I thought it was awfully crowded. I had been doing 1, well, let's see, usually you put it over here, so let me put it there. Okay. I realized I did something stupid, but 2, negative 1, negative 2. I didn't put my x's in. 1, 2, negative 1, and negative 2. Okay? Because when I did my x equal 1/2 or negative 1/2, I put it over here. It should have gone right here. Okay, so, and this produced a c of equal to 1/2. Remember that? And that meant your y-intercept, oh, we had a, and let me go back and do this now. I'm going to give Charles one more chance to choose his color.
Let's let somebody else pass.
What's that?
Somebody else give it a shot.
All right. Pick another color for our second one. Not red.
Green.
Green. Okay, we'll pick green for the second one. The second one will be y of 0 is equal to, what was it, 2?
Yes.
I believe it was. Okay. Now, this produced, this one up here, produced a c of 1/2, which well, no, I think I want black for a minute here. When c was 1/2, we had y is equal to 1 minus 1 over x plus 1/2, and that made x equal minus 1/2 our vertical asymptote. And that's what I mislabeled before. It was here. Okay? And your point was 0, negative 1, which was, this was in black, so let me go back to black. Goodness, this screen is driving my eyes crazy. 0, negative 1, right down here. All right, and we knew this was approaching the horizontal asymptote here, vertical asymptote there. It made it look so crowded before. The second one, the green one, thank you, Charles, okay, the green one here is 0, 2. That was this point. Okay, well, you knew it had to be approaching the horizontal asymptote here, but when you did that, do you remember what it was? Your new y was, your c was equal to, oh, that's what we were doing. Okay, yeah. Let's go back and do, I was trying to recreate what we were doing. Okay, and what we had here is that 2 is equal to 1 minus 1 over c. Now you suggested multiplying everything on both sides by c. So that gave you 2c is equal to c minus 1. Is that okay to do it that way? Subtract 2 from both sides, c from both sides, you get c is equal to minus 1. Right? Okay. So you came up the same way both times. Okay.
So I was just making sure that was like legal, I guess.
Right. Okay, so our new equation then is y is equal to 1 minus 1 over x minus 1. There your vertical asymptote is at y is equal to 1. Okay? And you had this point on it, so I was completely out of line. Okay? Nothing new here. Okay? There was your 2, so this means now you're in, I had it going the wrong way in everything. Can't believe how wrong I had it there. Am I still green? I think so. Okay. Here it's going up, and here it's going like this. So there was your second one. It shifted your vertical asymptote over here, rather than there to here, because it was a new function. Your 2, 0 now approaches that way, and this way. So then you're on that portion. When you had this one, it had another, and this is probably getting really confusing. And let me, if this will keep it from being too confusing. The other half of this function, the hyperbola, was like this, okay? We're not using that one because that wasn't only our initial condition. The other half of the hyperbola for the green one would then have been down here somewhere. But our initial condition was up there, so it wasn't here. But see, in both cases, increasing function has to be this with the initial condition made this your vertical asymptote. We always have that as a horizontal asymptote. When you change the initial condition, that changed your function, changed your c, the chi changed the vertical asymptote, and now this is in the upper quadrant. The lower quadrant we're not using because that's part of the domain we're not using. We're using this one, and this function has to be here, not using that at all. Okay? I don't know if that was helpful, but in every case they're increasing functions. Okay? And everything depended on what that initial condition was. Okay. Now, your solution curves, once you have the initial conditions, are then fixed to be that one for that one, this one for that one. The black up here is out of the question. The green down there is out of the question. Those are curves, but you have a whole family of them, but they're not the ones of interest. That's the one of interest here. There's the one for down here. Now, they bring up another concept here, and this is called attractors and repellers. Now, how are we doing on time?
30 minutes.
30 minutes to go?
We have
Okay.
But we're right on 10 a.m.
We're what?
We're right on 10 a.m.
Right on what?
10 a.m.
Oh, okay. And we go to 10:45, right? Anyone need to take a little break? Yeah, I think I do too. So this looks like a good place to do it. So I'm going to pause the slide here. All righty. Where we left off last time, we had just pretty much finished example 5. They may still have it linger. No, I think they're pretty much through with it. The next thing they're talking about are these attractors and repellers. So I'm going to clear this screen. I thought maybe I could use, I think it might be better just to clear, because that's so busy with other stuff. So, here's our supposition. Suppose that your y of x is a non-constant solution of an autonomous differential equation that we were talking about before, okay? C is the critical point of the differential equation. There are basically three types of behavior that y of x can exhibit near C. And I'm going to show those here. They show four, okay? And I guess one of them is duplicated. So we're going to do this. I'll use the bound here as 1. Let me get my pen back to black. Okay. Let's use this as 1. Okay. We'll use that as 1. This is 1. That should be a straight line. It's not. And we'll use this as 1. Okay. Now, we'll just pick a point here, 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 and here. These will be our C. They could be positive, negative, fraction, decimal. We haven't put anything in. Sort of ignore the x-axis for now. Okay? Now, in the first case here, alright, I'm going to do something else, and this may erase everything, but let me, yeah, it's fine. Yep, that erased everything. I put arrows here because I'm used to doing that on axis. Oh, that's part of it. Yep, that erased everything.
Now, are these C's, like, I know that you said C is the critical point, so are those
right.
lines you made, were those supposed to be asymptotes or something?
Say that one more time.
So C is supposed to be the critical point.
Right.
Well, I guess where it equals 0.
Where the slope equals 0. Yeah.
Slope equals 0. Does that mean those lines are the asymptotes?
Horizontal asymptotes. Because if slope is 0, that's a horizontal asymptote. Anything approaching here or here, or here or here, you know, it's going to be approaching that. So it winds up being a horizontal asymptote. Okay, they're not showing the two-dimensional part of this, just C. Okay, now the reason I want to take my arrows off, they're showing here the function is approaching here, and here's approaching there. Okay, on the second group, it's going this way and this way. Very fortunate I used the y-axis there. Here, it's going this way and this way. And here it's going this way and that way. Okay. These are the slopes other than, at C, the slope is 0. Okay. C, the slope is 0. I'll just write that in here so you'll see. C, because they're critical points, the slope is 0 there. Okay. Now, in the first case here, the slopes are negative above C, positive below C, so the C acts as an attractor. Okay. Both of the functions as x increases in value, then your it's attracting both of them. Here it's repelling both of them. Okay, it's already met the at C here, and it's going away from it. So that's called the repeller. This is a mixed case. Above it's repelling, but below it's attracting. Here, above it's attracting, and below it's repelling. So these two are similar cases. They're just going in opposite directions. This is your attractors. These are your repellers, and those are a mix of the two. Okay. When both arrowheads on either side of the dot labeled C point towards C, we're saying that's an asymptotically stable situation for the critical point, because in the long run, but things are going toward it. And that's called an attractor. Okay? When both arrowheads on either side of the dot are going away from C, the second case, that's a repeller, and that's called asymptotically unstable. As x gets larger, things are both going wacko in both directions. Wacko is not a mathematical term, by the way. Okay. When you got one coming towards C and the other going away from C, whether it's both up or both down, okay, then it's semi-stable. And that's all that was talking about. They do a lot more words, but that's what the bottom line is. Okay? Now, we're going to combine what we did in 2.1.1 direction fields with what we're doing in 2.1.2, which is autonomous equations. And so the middle of page 43, we're doing autonomous differential equations and direction fields. Okay? So let's clear the mess I've got here. Any questions on that first? Okay. Okay. If a first-order differential equation is autonomous, then we see from the right-hand side of the normal form, dy dx is equal to some f of y. Remember, there's no x dependence on the right-hand side. Okay? That slopes of linear elements through points on the rectangular grid used to construct the direction fields for the differential equation depends solely on the y-coordinate of the points. To put another way, linear elements passing through the points on any horizontal line must all have the same slope and are therefore parallel. Okay? Slopes of linear elements, blah, 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 along the vertical lines will, of course, vary. That's because whatever your y value is, okay? Let's just take the one they have here. We'll put this as being 1, 2, minus 1, minus 2. I'll go and put the others 1, 2, minus 1, and minus 2. Okay? If y equal 1 is your critical point, okay? And basically that turns out being a horizontal asymptote, so I'll go on and put it in red, horizontal asymptote. Okay? Y is equal to 1 is that. Okay? Let's go back to black, I think. Okay. Now, if you're doing your, and let's say this is a repelling type situation, so they're going in opposite directions, then whatever your slope is for this x, because that's only a function of y, it's going to be the same slope for every y value. Well, for every x value, I'll say. Okay? Because, and that's what they mean, the linear elements. Okay? Now, if it's a steeper slope up here, it's going to be steeper, but parallel every one of these. Okay? That's what they're getting at. Down here, it could be this way here, but it's going to be that way for every one of your, every variable x, as long as y is constant. Down here, if it gets a little steeper, then it'll be steeper for every one. Because it only depends, the slope only depends on the y value. So all these are going to be the same. Your figure in the book shows that. Okay? Now, there's another concept they talk here of the translation property. It says, you may recall from pre-calculus mathematics that the graph of a function y is equal to, so I think we're jumping a new rabbit here, so let's erase that. If you have a function y is equal to f of x minus k, how does that differ from y is equal to f of x? Shifted to the right k units. You're absolutely right. If the function here was like this, it shifts to the right k units this way. Okay? If k is positive. Okay? Okay? That's just a translation. And that's saying the same thing here. It's to the right if k is positive, to the left if k is negative. So if we go back to something similar to what we had, oh, here we go. Here's a differential equation. Let's clear that. And this is not a new example, but it's sort of mixed in the text here. dy dx, that's an ugly dx, isn't it? Is equal to y times 3 minus y. Okay? Now, tell me something about that. Is there anything you can do right off the top about that?
I can tell you it's not linear.
Very good. Excellent. Okay? And that is true.
Would it be second order?
Not second order. dy dx is first order.
Oh.
First derivative.
First order. What's first order?
What kind of differential equation is this?
Ordinary.
It's ordinary, it's first order, and nonlinear. We know those. But does it have any other feature? The only place, the derivative only depends on the dependent variable. So what kind is that? Talking about for a day and a half now. Autonomous.
Autonomous.
Yes, that's an autonomous differential equation. Now, what can you tell me about any of those values significant?
Y can't be 3.
Can't be 2, is that what you said?
3.
3? It can be 3. But what would it be if y is equal to 3? That's a very good point to pick.
0.
What would be 0?
Y.
No, if y is 3, it's not 0. Okay. If y is 3, y isn't 0, okay?
The derivative.
The derivative is 0. And what's true about derivative being 0? Horizontal asymptote. Okay, this guy over here in the, okay, never mind. Okay, so y is equal to 3. What we're going to call that is, this time we'll use this, that is a critical point, right? Let me do it in red. It's a horizontal asymptote. Y is equal to 3. Okay. What else? Any other critical points? Yes? Yes?
0.
0! Yes, y is equal to 0 is also a horizontal asymptote or a critical point. Okay? Now, sort of a, like they said, sort of a special case of what we had before. For y's very large there, very large y's, like greater than 3, this will then be negative, that will be positive, so your derivative is going downhill, right? So this is not a bad thing to put on your graph, is that this is coming downward there, right? Negative slopes. Anytime y is greater than 3, then this will be positive because it's greater than 3. But this will be negative because 3 minus y will be negative. Yes?
Well, I have 2 questions.
Okay.
First one is, if you multiply the y's together, you get a parabola, right?
Yeah, that's going to produce a parabola. Right, well, your derivative would be a parabolic shape. Okay.
And then if we
Function won't be a parabolic shape.
And then if we took the antiderivative of that function, would there still be a horizontal asymptote?
Probably not, but who cares? Is what I would say. I mean, I don't know. I mean, what were you getting at there?
Like the original function. Like I know that it says that's the derivative equals y of 3 minus y.
Okay, so this, yeah. Okay.
It says the derivative is equal to y over 3 minus y.
Y times 3 minus y, right. Okay. Yeah. Now, what all we're interested in now is where is the function heading? What is the function doing here? Okay. This tells you where the slopes are. There's 0 at y is equal to 3, 0 at y is equal to 0. Okay? Now, they're all some direction here. These are 3 regions now. 1, 2, and 3 regions. They're all going to head the same direction in each region. I just started with that because it's pretty obvious. When y is greater than 3, this is going to be positive, because 3 is positive, and that's positive. Okay? But this will then be negative because y is greater than 3. So the product of these two will be negative, meaning your slope is going downhill. So all the curves up here have to be sloping down. Approaching 0 here. Okay. Now, let's take the middle portion. Y between 0 and 3. Well, y is still positive, right? Okay? But this is positive because y is between 0 and 3. 3 is greater than y. So this is positive. So they're all pointing upward here. But they have to be horizontal here. So these should be families of curves like this. Okay? They've got to be. So this slope is upward. Okay? Now when y is negative, okay, less than 0, this of course will be negative, right? But 3 minus a negative number is going to be a positive number. But this will be negative times positive. The product is going to be negative. So they're downhill here. Okay? So, for what it's worth, this asymptote is an attractor. This one's a repeller. But who cares? I mean, they're just names. That's why I couldn't figure out why they spent any effort on that, but they did. But what you can do now is draw in curves that fit the bill. We don't know where it's going up here. Whatever it's doing is going to be approaching here. Okay? Yeah. Here, it has to be going like this. Okay? And those are just what they're called horizontal translations. Here we're going like this again. Okay, because they have to be sloping downward but approaching in the negative direction, your horizontal asymptote. Okay? This function, whatever it is going to fit some curve like one of those. If it's in region 1, it's going to be on a curve that's going like this. In region 2, it's going to be on a curve that's going like that. And in region 3, it's going to be on a curve that's coming like that. Has no choice, okay? In any one of those parallel curves, and you have an infinite number of them in every place, will contain, for any initial condition, you pinpoint that. That's your function. The others are immaterial. Is that right? Is that understood? Make sense? Okay. If y of x is a solution of an autonomous differential equation, dy dx is equal to some f of y, like that one that we have there, then y1 of x equal y of x minus k, where k is a constant, is also a solution. Basically, is what I was just saying. Whatever this shape is, I just drew it like this. It has to be approaching this as a horizontal asymptote. It could be going down rapidly, it could be going down slowly, it could be doing whatever, but it has to be approaching this. This one, same deal. It can be very abrupt, or it can be very slow. It can be gradually slow. Whatever the slope is, then all your other solutions are going to be parallel to that. Are going to be just like I tried to draw these to be pretty much parallel to each other. Draw any other shape that fits the bill here. This could be something like this. Then all of them would have to be like that. This could be something that goes. Then all of them would have to be. And every translation of it would then also be a solution. Not for a initial value. If you have an initial value, ping in on one of them, all the rest of them are out of the picture. Okay. So, let's do another, and this is an embedded example, you might say. They say here, it's easy to verify that y of x equal e to the x is this is good for minus infinity less than x less than positive infinity. That's good everywhere. I lost it. Here it is. There it is. Okay. That's a solution to this. dy dx is equal to y. Autonomous equation here. A very simple one too. And it's pretty obvious. Take the derivative of that and what do you get?
E to the x.
E to the x, which is y, right? So the derivative is equal to the function. So that's obviously a solution. Okay? Is it the only solution? No, of course it isn't. Then you do any horizontal translation of that, which would be y of x is equal to e to the x plus k. That's also a solution. Because guess what? Take a derivative of this, and what do you get? E to the x plus k, which is also y. So any horizontal solution, to the right, to the left, it doesn't matter. Those are all, that's your family of solutions. Okay?
I'm sorry to interrupt. What page are you on right now?
This is on page 43.
Is this on the translation?
Translation property. Underneath the red line that said if y of x is the solution, the one right below that. Right at the very bottom of that page.
Okay.
You see it?
Yes, sir. I'm sorry about that.
No problem. So what they say here, y1 of x, if that is one solution, this one up here, another solution would be y of x minus 5, just for instance, which in this case would be e to the x minus 5. That's going to be a solution. In that case, we go 5 units to the right. It's a parallel curve, and it'll also be a solution to it. Your initial condition pins in on which is the actual one you're interested in. Okay? So your most generic form would be e to the x minus k. We have finally finished section 2.1. Under direction fields, do any of the odds that are in the back of the book, 1 or 3. In 5 through 11, it says use computer software, but see if you can do it without it, especially the easier ones. Do any of those that are in the back of the book. Then do number 13, if that's in the back, and do 15 if that's in the book. Now 15 deals with isoclines, and we were talking about those before. with topographic maps, right? Remember that?
Oh yeah, the surveys.
Right. And now then there's some discussion problems. Usually those aren't in the back. If any of them are, consider those. Then in 2.1.2, these should be in the back. Number 19, you should be able to do that one if it's in the back. Any of the odds 21 to 27 if they're in the back. 29 if it's in the back. Then the discussion problems usually aren't, but if you find some that are, you certainly can do that. And then they do a few with mathematical models that we talked about, a population model, a terminal velocity, or those kind. Chemical reactions, because some of you love your chemistry so much, those are all given there too. Now, I can't believe it, but we're finally at the point where we actually start solving some differential equations. All right, it's been too long. Okay, shouldn't have done that. I should have just done to here. Okay. Now, 2.2 starts off with one type of first order differential equations, and this is the first thing you try anytime, and it's the easiest to do. It's called separable equations. Okay? And it's called solution by integration. It says consider a first order differential equation, dy dx is equal to some f of xy. Okay? Now, what we were looking at before for our autonomous, x is not dependent on x, that's just dependent on y. What we're going to consider first now is when there's no y here, and it's strictly a function of x. So we're going to narrow this down to just do some g of x. Okay.
So if we're solving for just x now, not y, does our dy dx change, like independent over?
Okay, now say that one more time.
If we're just focusing on x now, would we take the y out of the dy dx?
No.
Oh.
That's your differential equation. Y is a dependent variable, but your derivative doesn't depend on y, it only depends on x. The y is still in there, but the derivative doesn't depend on y. Okay? Now these have great potential for being solvable. And here's why. Let's just go down to this, dy dx. Now I'm going to do something that it sometimes drives pure mathematicians absolutely crazy. Okay? This is what it looks like we're doing. Multiply both sides by dx. Okay? See, that's an operator. That's not a fraction. But you can sort of treat it as a fraction. The other way of saying this is write it in differential form. That would be dy is equal to g of x dx. Right? Isn't that sort of saying the same thing? It's just writing it in differential form. Okay? Now, if that's the case, integrate both sides. Now, of course, g must be integrable. If g is not integrable, you're still stuck. Okay? But if it is, all you have to do is integrate both sides. And the integral of a dy is just a y. Right? And the integral of g dx, g of x, is basically going to be some capital G of x, and then if it's indefinite integral, you put a plus c on it. That's how you do these differential equations. It's pretty easy, pretty straightforward, and doable. Okay? Here's an example that's not an example, okay, not listed as an example, but it said, for example, if dy dx is equal to 1 plus e to the 2x, okay? how would you go about solving that?
Take the antiderivative.
Okay, we'll write it as dy is equal to 1 plus e to the 2x dx, and integrate both sides, and this will be a y, and this will be a y. Antiderivative of 1 is x plus 1 over 2 e to the 2x. Perfect, you're really good at that. And then put a plus c on it. Okay? And that, sure enough, is your, that's just for funsies, let's take the derivative of both sides. This would be dy, or dy dx, be 1. Yep, that's what you got there. The derivative of this would be 1 half e to 2x times 2, which equals e to the 2x. Yes, that's it. Okay? The c would then be your constant of integration, or your parameter. So it's x plus 1 half e to the 2x plus c. Now, let's go back to our first case, dy dx equal f of xy. Now, if that function, f of xy, is some g of x times h of y, in other words, if you can separate the x's from the y's completely as two different functions, usually this is done by multiplication, but it could be done by addition. If you can separate them any way, you can't do it by addition and subtraction. That doesn't work. If you got a x added to a y, there's no way to separate that. X multiplied by y, yes, possible to separate those. X divided by y, yes, possible to separate those. X subtracted by y, no, not going to be able to separate them. But if it's in that form, then this is called a separable equation. Okay? If you have that, here's basically what you do. dy dx is equal to some g of x times h of y. So let's see. dy dx equal to y squared x e to the 3x plus 4y. Okay? You reckon that's separable or not?
Even if it's not separable, could you just do integration by parts?
Maybe you could. I'm not sure I could, but maybe you could. That's a pretty tough one. But no, that's... Okay, you're in Cal 3 too, right? We haven't got to multiple integrals. You would have to almost have a multiple integral there.
Oh, but I know how to do it.
You do?
Mm-hmm.
Okay.
I know triple integrals too.
Triple integrals, okay. This is a ordinary differential equation, not one that would be appropriate for, I don't think. So, is it separable?
I would say so. That's exactly.
Okay, tell me how to separate it then. Okay. Well, you do too, but you just don't realize it. Okay. Y squared x. Those two I know are separable. The part that bugs you is the one with the plus in it. But you see, that's in an exponent. What do you have if you have the same base, this happens to be e, raised to the sum of the exponent? What does that tell you? What's that equal to? Okay.
Well, wait, could it...
What if we had...
Is it e to the 3x times e to the 4y?
Absolutely. That's e to the 3x, e to the 4y. Anytime you have the same base, different exponents, keep the base, add the exponents. So undo that, and now this is separable. You can separate this to be y squared e to the 4y times x e to the 3x. Those are separable by multiplication and division, or division. Not by addition and subtraction, but you see, because that's in an exponent, you can make that separable. Okay? Now, what would you do next? This is your dy dx. You separate them, okay? You write this in differential form, pull the dx over here, and then divide by your y's. Y squared e to the 4y. Divide both sides by that. You've already pulled that over, and y squared e to the 4y. Now, this then, you try to integrate that. Now is a possibility for integration by parts. Okay? Don't know for sure if it'll work, but that would be possible there. Over here, yeah, possibly integration by parts there too. In fact, this one not, because that's a division problem. That one's a real bear. So I don't know. It's separable, but it still may not be integrable. Okay, but yeah, you get the idea. That one is separable. You get all your y's on this side, all your x's on that side. You separate it. That I know we can do. Might take a while, but it's integration by parts. This one, since it's in the denominator, oh boy. You want to maybe try a substitution or something, but I don't see anything that's going to work super well on that. I was going to suggest a little bit partial fractions, but I don't think they work with exponentials. You could try it.
I do have a question. Is it written on the left side of the equation dy divided by y squared e to the 4y?
Yeah, the left hand side is dy divided by y squared e to the 4y. The right hand side is x e to the 3x times dx. So that's why I said this one's integrable after a while, probably by parts. Okay, this one pain in the neck.
That one would be like, would that be partial decomposition for that one?
That's what I would try, but you see, that works, I know for polynomials. I don't know if it works for exponentials. I've never seen it work for exponentials.
You guys check the back of the book.
Huh? Oh, wait. No, whoa. Think of this. Right, this is y to the minus 2, e to the minus 4y. Now that may be integration by parts. Yeah, you have to do it the opposite way you did that one. Because you see this one, you're taking derivative here, it makes it disappear. Taking derivative of this, if it's to the minus 2, that makes it worse. So this would have to be the thing you integrate, and that's the one you differentiate, I think. But we're not worried about that now. We only want to know if they were separable or not. And this was. Let me just quickly put this one down. dy dx is equal to y plus sine x. Separable or not?
Yes.
Why? How?
One's sine x and one's y.
Okay, but those are added. They're not multiplied. See, that one, even though the exponents were added, you could write it so the functions were multiplied. This one you cannot. This is not separable. Yeah. Okay? Because you can't multiply or divide by getting it. Okay? The first of those is separable, the second non-separable. Okay. All right, I think we've completely run out of time, right?
10:47.
Yeah, sorry about that. No extra charge though. Okay. We'll start top of the next page and go from there. Let me see if we got far enough for you to do any homework problems here. Nah, we haven't actually solved any, so just focus on the others and your test, and we'll pick up from there. This is a pretty short section. We'll probably finish it next Tuesday. Remember, no class on Thursday for us, anyway. If you have other classes, they're meeting. They're not going to take off a day because I have an operation.
No, I don't feel like.
Yeah, okay. Yeah, you don't have to go to chemistry either. Okay.
I guess I don't want to.
Okay. All right, good deal. We'll see you next week. Sorry about the missing a day. Yes. You gave me your test and the paper, right? Is that what you were asking?
I mean, in the previous time, I think our.
I'm sorry?
Week, did I give you my paper?
What about it?
Did I give it to you?
You gave me the research paper last time and the test this time. Yeah. Yeah. I haven't got it graded yet.
No, I was making sure because I didn't know. I didn't realize. I had something wrote down in my notes
Right.
about the paper topic.
Right.
And I just lost my bearings.
Yeah. Okay.
My
Yeah.
anxiety, that's all.
Yeah. You gave it to me last time. I got one paper graded this morning before class, but I ran out of time before I got to yours. So now I've got your paper.
My test, I put everything on paper.
Yeah, I saw
I
that.
just taped it
Yeah.
together.
Right. Good deal. Thanks.
All right. Well, wish you well on your